Logo working, RGB on point. But behind this result was a lot of struggle. Let's rewind. The first step started on paper. We sketched the logo on 0.5 centimeter grid paper to ensure perfect symmetry, keeping every single dimension calculated from the very beginning. From paper to SolidWorks, I started with a 2D sketch. The best part about these dimensions is that I can change the scale or size at any time, and it will keep its perfect symmetry. Then, I turned it into a case that opens and closes to fit all the components inside, and added 2 openings for the switch and the charging port. To get it ready for printing, I moved it over to the Anycubic software, and this is how the layers look as the piece gets prepared for printing. And here is the printed logo. The finish looks incredibly clean, exactly how we designed it. The case opens and closes smoothly. Now, let's move on to the fun part, the electronics. Here are the components we'll use to build the system. The ESP8266 microcontroller for Wi-Fi control, along with a 12-volt common anode LED strip for the lighting. For portable power, we have a 3.7-volt lithium battery, its holder, and a simple power switch. To regulate the power, we'll use a step-up converter to boost the voltage, paired with a power bank module for charging. And to assemble the circuit, we have a prototype perf board, a TIP122 transistor to handle the LED load, and a 1K ohm resistor. I started here by placing the 3 transistors in their designated spots on the board. I put them down first to adjust the spacing, and right after that, I went straight into soldering their pins to ensure a solid mount and a stable connection. And that's the entire circuit. We start by drawing the battery, running the positive and negative power lines, and splitting them to both the power bank module and the boost converter. From the power bank module, we run 2 power lines to the ESP8266, connecting to VIN and GND. Next, we map out 3 control lines from the ESP, D1, D2, and D5. We draw 3 squares for the 3 TIP122 transistors, each having 3 pins from left to right, base, collector, and emitter. Now, full disclosure, I actually got mixed up and flipped the connection while drawing this part. Scientifically, for an NPN transistor, the emitter pin is the one that connects to the ground line, while the collector pin goes directly to the RGB color channels of the LED strip. We connect the digital control lines straight to the base of each transistor. The positive side of the common anode LED strip connects to the 12-volt positive output of the converter, while the negative output goes directly to the main ground line. And here is a critical point. You must tie all the grounds together to create a common ground. Without this common ground line, the signals won't have a reference point to complete the circuit, and the system won't work at all. This is the complete system, with all the components and wires tucked inside the case we made. Since this was my first time using this type of board, the soldering turned out, well, let's just say it looks like I did it with my eyes closed. Because of that, a buzzer test with the multimeter was absolutely necessary to make sure there weren't any short circuits caused by those solder joints. And the result? No short circuits at all. After that, I measured the voltages to check the battery level, the output from the step-up converter, and the operating voltage for the ESP. Everything looked perfect. Time for the coding and programming. Here, I programmed the ESP8266 to connect to the home Wi-Fi. This means any device on the same network can control it. Literally, if your smart fridge is connected to the Wi-Fi, you could control the logo from it. To make the system fast, I set up a protocol that allows the ESP to remember the network and reconnect instantly upon power-up, instead of scanning for available networks every single time. It only does the full scan the very first time. I also built a web page with a static IP address. Whenever you type this IP into the browser of any device on the network, it opens up the control interface immediately. Time for the final assembly. Now that we're sure the connections are good, we started putting everything in place. The components were a bit of a tight squeeze inside the case, but the important thing is they all sat right in the end. One final closure, and now for the moment we've been waiting for. Let's test it out. By the way, here's a quick side note that wasn't in the original circuit diagram, but I added it during assembly. I placed a capacitor near the ESP8266 to keep the voltage stable. This prevents the board from resetting and losing connection when switching colors due to sudden voltage drops. Let's see the action. Once we turn on the switch, the device boots up and connects to the Wi-Fi right away. We type in our static IP from the phone, and the web page loads in seconds. We can control the power and switch between red, green, blue, yellow, purple, cyan, and white. I have no idea why the white color looks so sick and washed out. This LED strip is clearly crying for help. But it's fine. The main thing is the system works, and the other colors look spot on. And that's it. If you like this smart system, don't forget to like and subscribe. Let me know in the comments how we can improve this circuit. See you in the next project.